Welcome everyone. Today, my name is Karthik from Applied Mechanics Department, IIT Delhi, and my case study topic is application of composites to satellite structures. Here we can see a list of contents which will be discussed in the upcoming slides. The basic introduction, what is a composite and why we need to use it, applications of aluminum matrix composites in satellites and the related research, and some references at the end. Now, what is a satellite? A satellite can be a machine or a planet orbiting around another planet. It can be an artificial or a natural satellite. One example of a natural satellite is such as Earth's as moon. Sputnik 1 is the world's first artificial satellite launched by Soviet Union on 4th of October 1957. After that, around 40 countries have launched around 8,900 satellites. According to an estimate, around 5,000 satellites are remaining in the orbit, and out of which 1900 were operational, while the rest had exceeded their useful lives and become space debris. Now, the basic anatomy of a satellite. A satellite have 6 major components generally: structure, payload, attitude control system, thermal control system, power system, and the propulsion system. And in the adjacent figure we can see a satellite with propellant tank, reaction wheel, TTC antenna, thrusters, high gain antenna, and an array of solar panels. Now we will discuss all these parts one by one. So first is reaction wheel. A reaction wheel is used for 3-axis attitude control of the spacecraft. It is independent of rockets and external applicators of torque. They provide a very high pointing accuracy, and they are used whenever we are required to point a telescope or a camera at any particular object in space. Next is propellant tank. It is a container used for storing a propellant. Solar array. It is a group of solar cells, solar panels attached to the satellite. It is used for running the sensors, active heating, cooling, and telemetry, and can also be used for electric propulsion or solar electric propulsion. For primary means of communication, high gain antenna is used. Next is thrusters. It is a propulsive device used for station keeping and attitude control in the reaction control system. Next, TTC antenna. Telemetry, tracking, and command are the vital functions of a spacecraft. The ground station and the spacecraft communicate with each other through this TTC antenna. Next, we can see the whole journey of a satellite. So satellite has to travel from all these 5 layers of the Earth's atmosphere. First is the troposphere, then stratosphere, mesosphere, thermosphere, exosphere. Then exosphere is the uppermost region of the Earth's atmosphere. Next, we can see the 4 orbit stages of a satellite. First is the circular low Earth orbit. Second is the Hohmann elliptical transfer orbit. Third is the intermediate drift orbit. And the fourth is the circular geostationary orbit. Now, what is a composite and why we need to use it? A composite material is a material which is produced from 2 or more constituent materials. The constituent materials with dissimilar physical and chemical properties are merged together, and after merging they make a material uh, whose properties unlike with. So as we have seen, the temperature change in the outer space changes from -90 to around 80 degrees centigrade, and the satellite has to travel from these temperature changes. So it has to satisfy these extreme diverse extreme and diverse requirements of the outer space. Now, composites, due to their multifunctional, multidirectional, and tailorable properties, have revolutionized the space industry. Now, the aluminum matrix, fiber metal laminates, metal matrix, polymer matrix, and ceramic matrix composites are used in some components of the satellites due to their lightweight, dimensional stability, high specific strength, thermal stability, tribological properties, and diverse material combinations. Now we will see some of the applications of aluminum matrix composites in the satellite structures. Now, aluminum matrix composites, on one side, they have the applications areas such as mountain bikes, golf clubs, and marine yacht fittings on one side, and on the other side they are used in defense and aerospace applications, electronic housings, and satellite structures. On the right side, from the reference 13, we can see a multi-inlet fitting for a truss node. Due to their tailorable coefficient of thermal expansion, aluminum matrix composites are used in some of the electronic packaging applications, as we can see in the image from reference 13. These composites have massive applications in satellite structures as thermal planes, truss nodes, housings, bushings, longerons, EMI shielding, and electronic packages. From reference 14, we can see the comparison of metal matrix composites for heat spreading material. If the initial structure of AL 2024 is replaced by 6061 T6 aluminum reinforced with 10% germanium, the 42% rate reduction was achieved, and by replacing the former again with the 6061 T6 aluminum reinforced with 30% particulate silicon carbide, 70% weight reduction was achieved. Aluminum reinforced with germanium have proven effective for heat spreading material. It will provide thermal conductivity close to copper and the coefficient of thermal expansion close to silicon. Now in satellite payloads, aluminum reinforced with graphite epoxy tape was used in hybrid horizontal cross arm of Intelsat 4. This combination was used due to low weight and minute deflections required from the arm in service. Aluminum honeycomb with graphite epoxy layer as reinforcement was also used in ANIC, which was a Canadian communication satellite. This combination is validated for good structural stiffness, minimization of thermal distortion, controlling the effects of solar radiation. Next, in satellite attitude control and power systems, the high gain antenna boom of Hubble Space Telescope was made by germanium or aluminum 6061 reinforced with P100 graphite fibers using diffusion bonding. This combination was selected due to good electrical conductivity for wave guidance, low coefficient of thermal expansion for robust movements, etc. A filtering capability was enhanced for the entire 100 Hz frequency range by incorporating 6061 T6 aluminum reinforced with 10% germanium and 6061 T6 aluminum reinforced with 30% particulate silicon carbide. By incorporating aluminum reinforced with germanium, a vibrational filtering proficiency improved by 7.2 decibels, and by incorporating particulate silicon carbide, filtering proficiency is improved by 3.62 decibels. Next, in satellite thermal control systems. In microwave systems of the satellite, aluminum reinforced with silicon carbide can be used. For high performance thermal applications, aluminum reinforced with alumina, silicon carbide, and tungsten bromide can be used. For those applications which requires exceptional thermal characteristics and dimensional stability, Nanoparticles of silicon carbide can be used for reinforcing the aluminum. These combinations were preferred due to their diverse properties such as effective dissipation, minimum thermal stress retention, low coefficient of thermal expansion, etc. For thermal management of microwave housings, aluminum reinforced with silicon carbide can be used, and for thermal management of the printed circuit boards, aluminum reinforced with boron can be used. And in the figure below, in the table below, we can see the relevant properties of the materials which we have discussed so far. For heat sink and heat transfer applications in satellites, aluminum reinforced with 5% volume aluminum silicate and 50% volume reinforcement of carbon fiber using powder metallurgy can be used. Aluminum reinforced with graphite and aluminum reinforced with particulate or whisker silicon carbide can result in high heat dissipation, no outgassing, high stiffness and strength respectively. The next application is in satellite propulsion system. Titanium based turbine blades and compressor fan blades can be replaced for cost effectiveness by aluminum reinforced with boron. These aluminum matrix composites are not only lighter than the titanium counterparts but also provide the following advantages such as reduce the compression cost, good impact resistance, provide dimensional stability at high temperatures, etc. Next is the related research in this context. By incorporating nano and hybrid reinforcements, the resultant properties are much better as compared to micro reinforcements. But there is a major issue of homogeneous dispersion of these reinforcements and is difficult to control, resulting in the agglomeration of the particles, which makes the bulk production difficult. Such structural components are still in research and development phase. Here we can see all the references. Thank you.